Let's go ahead and get started. Oh, I like that. I like that. Thank you. Was that Taylor?
That was Ryan every time. That was Ryan's.
Ryan? Oh, Ryan. Thank you, Ryan. Well, whenever I turned, you're smiling and he's just acting normal. So I don't know which one of y'all it was.
Oh, okay.
So today we're going to cover hashing, which is one of the most important features in data structures. And it'll lead to hash tables, which for some people consider the most important data structure there is and is the one you should always default to. I, of course, don't go to that extreme, but hashing and therefore hash tables do have a lot of properties that are very
So what's your go-to
advantageous.
if it isn't that? What's your go-to if it isn't that?
I prefer to assess the situation, aka it depends. You know, there is no silver bullet. Also, you can bubble sort. Also, I prefer a level of indirection, so if I want to change it later, I can. That's really what I prefer.
You not change hash tables, did you?
What's that?
You not change hash maps easy?
Hash maps? Change
Hash
it?
tables.
Well, you have an interface you're trying to adhere to. You just want to make sure that you can, if you want to switch from hash tables to a binary tree or something, it's very easy to do so. So just code that way.
Okay.
And then if there's an issue, fix it later. But just make sure you fix your code so that it can be easily refactored or maintained. Yeah. Anyways, hashing. All right. Real quick, high level. Hashing, it's really just going to combine the advantages of an array and a linked list into one data structure. So real quickly, what's the advantage of an array?
Easy to access
Quick random access, right. But what's its downfall? Yeah, trying to insert somewhere in the middle, not very good. And to some extent, memory. And then a linked list, on the other hand.
Memory is good for.
Yeah, you have to search. You can't do a binary search or search real quickly. But inserting is, once you have the address of where you want to insert, it's pretty quick. So we're going to try and combine the two. Well, really, that's the first way of doing hash tables. The second one is just use an array for the whole thing. But we'll get to that later. I think hashing with chaining or linked lists is a lot easier. Okay, first off, most of the time hash tables or hash maps are used to map things. In Java and in C++, we call them maps. Other languages like C# we'll call them dictionaries. Whatever, they're the same thing. But the idea is you have a key, and that's going to map to, hopefully, a value. So it's a key-value pair. And I think I erased it on the board, and we had it already. So what was an example of doing this?
Student to ID.
Yeah, student to ID. So you might have, we'll just call it hash table. What should we call this? No one? All right.
Hey.
We'll call them students. Student names, there we go. And wow, that's way too many letters. We'll call it SN. There we go. So you can do SN. We'll go ahead and put maybe their ID, which is 1, 2, 3, 4, 5, 6, 7. And this time we're mapping a ID to a string. So you're asking for the name. What do you want this person's name to be? John Paul. All right. Okay. And let's do the other one. Equal to Bruce. I'm just hearing random things. So I heard Bruce Savage up here. I don't know if that's what anyone actually said. So the idea, Randy Savage. That's funny, that's still out there. So we see out SN, so 1, 2, 3, 4, 5, 6, 7. What should it print out? John Paul. All right, so this could have easily been done with arrays. So let's switch them and do student IDs, because no one stopped me. Oh, they're SIDs. That doesn't sound right. Anyways, John Paul. 1, 2, 3, 4, 5. All right, I'm tired of writing. And then we have, what was it, Bruce Savage?
Yeah, Bruce Savage. That's my boy.
5, 4, 3, 2, 1. And we do 5, 4, 3, 2, 1. What is it going to print out?
Bruce Savage.
Actually, it doesn't print out anything. That's an error. Ha-ha! All right, there we go. Now what is it going to print out? 5, 4, 3, 2, 1. There we go. Okay.
Sick.
You don't know. It may or it may not. All right, so we have some keys. What are the keys in this example? The names, right. And then what's the value that they're mapped to? The ID. Keep in mind that these could be classes as well on each side. You could have a student class and then map it to, I don't know, in car class or whatever, figure out what car they have. All right. All right, so slides are going to talk about, going to try and derive this a little better about explaining why arrays and linked lists, kind of combining them is advantageous for this structure. But first off, so far we want a structure that finds and searches are very fast. Hopefully so far you noticed that arrays, well, searching is still binary. No, that's sorting. Sorting is different than searching. Binary search, binary tree can hopefully, binary search is log n, binary tree can hopefully guarantee log n. But we really want to be as close to O of 1 as possible. And of course, we don't want to execute very many instructions because we want this data structure to be as fast as possible. All right, and of course, we want inserts and deletes to be fast too. Wow, we're demanding. And then objects in the map, in maps, should have unique keys. All right, so that's another thing. We'll just say right now that all the keys are unique. So what have we looked at so far? Well, arrays, we can kind of sort of accomplish searching at O of 1. Maybe not with up there, but if we had it reversed, we could just create an array that was huge, and then we just map that number to a certain string and everything else would be null. Okay, we could do that, and then your search time would be O of 1 because you're just jumping to the right memory location. But not very space efficient. Hopefully you can tell that there'd be a lot of wasted space if we did that implementation. Binary search trees, well, we can do everything in O of log n time, which is good, but we're searching for O of 1. So binary trees might not be that great, or it's not exactly what we're looking for. They're good, but they're not what we're looking for. Hash tables, the generalization of array that under some reasonable assumptions, aka in the average case, O of 1 for insert, delete, and search of a key. So if we end up relaxing our requirements and not requiring O of 1, and just say for the average case O of 1, hash tables can actually give us this. But let's go back and talk about the array approach just to make sure it's clear why doing with just a pure array is not the best thing. Let's go and pretend we want to store everyone's, we have a database and we're storing everyone's information in the entire United States in an array. And we want to sort them by their social security numbers. We could try and have an array to hold all the references, so 0 to a billion essentially. And then use SSN as the key, so you have O of 1 access that person object. Well, that's great. Fortunately, the number of keys is much less than the array. In 04, it was a little under 30 million. Now I think it's about 320 million. Yeah, we keep growing.
Because they're dead, or just because they don't have an assigned social security number?
So the population of the U.S., sorry.
Oh, okay.
Yeah.
Less than that.
In 04, it was just a little under 300 million. Now I think we're up to 320 million.
Okay.
Yeah, something like that.
Dang.
Roughly 60% of the array would be unused. Good or bad?
Bad.
Terrible. All right. But we would get O of 1 for searching, right?
Hey,
Yeah.
all
Hey.
right.
So it's not. Maybe it's not all that bad. Okay. All right. In comes hash tables. Hopefully good for storing and retrieving key value pairs, not good for iterating through lists of items, storing objects. All right, let's go start actually talking about this. Maybe we have hashing, or we'll look at it this way first. Sure, why not? All right, so the idea of a hash table is you will have your array, and your item is going to map to some part of the array, but keep in mind that what you're actually mapping to is called a bucket, and that bucket can store multiple objects. So in this example, index 7 is storing object 1, which has a key of 15. Notice that the key of 15 is greater than the length of the entire array. Let's see, index 6 and 5 are empty, but 4 is mapping to 2 objects who have 2 different keys. Object 3 is empty, object 2 and 1 only have one object, or I'm sorry, index 2 and 1 only have one object, and then index 0 has no object. Excuse me. All right, this picture makes some sense? All right. How could, that is a great question. What could we use to make it point to 2 objects? Or 0 or more objects?
The what? Like what objects?
Make a class that holds them.
We could use another array, but maybe it only has 0 objects. What could we use instead? A linked list. There we go. So in that implementation, you just have an array of linked lists. There are other implementations, but that's a good way to start it off. Yes?
Oh, so I was gonna say, you have these keys that are basically, so if you wanted to retrieve, you'd have to use the value of your array to point.
Yeah, hold on. Let me see if I can give you the quick example of how this was accomplished. Okay, great. They took the key, they did modulus of the length of the array. Length of the array is 8. What's 15 mod 8? 7.
How can you store 2 objects if they're not part of an array then, like into a table?
Well, it's not an array, it's an array of linked lists.
Oh, okay, that makes sense.
So notice 4 mod 8 still 4, and then 28 mod 4, I mean mod 8. That should still be 4, hopefully, unless my math died.
So would you call for
2.
that? Would you call for the value and to get the object, or would you just call for the key to get the object?
You would pass in the key, and it would try and find the object. Let's say you did key 28. It would immediately jump to 4 and realize there's multiple objects. Then it would have to walk down the linked list to find the correct object, comparing your key to each one here and then returning it.
All right, so you wouldn't just go 4 and bring to 2 objects.
You would jump to 4 immediately.
No, I'm saying you wouldn't, like, you said you call for the key, so you wouldn't just call the value 4 in the linked list array, and then it would send you to the object.
Okay, yeah, I want to say yes, but just to be specific, you would have to walk the linked list in order to find it. Okay. Well, that was epic foreshadowing. All right, don't know why these slides are messed up, but they are. So they solved this problem by using a much smaller array and mapping keys with a hash function. All right, basically you're going to take all the possible keys and then map them to some number that is within the size of the array.
The universe.
Yep, the universe of keys. We have a lot of universes, maps to different ones. There we go. Hey, look at that. Maybe key 1 maps to 3, key 2 maps to 2, key 3 maps to 3, key 4 maps to 7, key 6 maps to 5. Notice they don't have to be in any particular order. They just have to map around. Oh, hey, look at that. Great. So the hash value or index is used to index into the array or the hash table. And what a hash function does is it takes a key and returns a value. All right. Important that the key remain constant for the lifetime of the object. Yes. That hopefully will make more sense in a little while. So here's some examples. Usually when you do your when you do your hash table, there is a hash function that's going to convert your key into an integer. It always must convert your key into an integer. So if your key is a string, you must have a function that converts a string to an integer. If you have whatever class it is, you must have a method to convert that class to an integer. And then the simple way to do it, well, right now is if you have a key, after you get the key and the item type, you run the hash function on the key. Notice the key can be in any type, but you get a hash value. Then you go to the table of the hash value and set the item. At least in this example, yes.
Is there any general name for, like, if you were to do it in the STL with objects, is there a general name for the function you would?
Yeah, you would have to overload something.
Okay.
I don't recall off the top of my head what that function is. Okay, so if you look at this code for insert, let's see. Jumping to some position in the table that's O of 1, and then putting an item in O of 1. So really you're concerned about the efficiency of the hash function is what we're trying to point out here. So the efficiency of using a hash table is based upon your hash function. Do y'all see why that's the case? Okay, great. We want it to be fast, create a good distribution. That'll make more sense when we have an example. And can use as input for different parts. Okay. Very common to use modulo. Did y'all did modulo in procedure, right? You do the integer division, modulo is the remainder. We call it modulo, you call it modulus. Okay. Modulo, modulus, remainder, it's all this. Yeah. So hopefully 8 mod 5 is 3. Y'all good with that?
I'd love that.
You can live with that? Oh, good. I'm glad. 11 mod 5 is? 1. All right, we're doing great. Notice that there can be multiples of m that give the same result, 0. But multiples of other numbers do not give the same result. In other words, so what happens if m is a prime number where the key is multiple of m? Okay. Come on, please just give me an example. Here we go, perfect. All right, let's pretend we have a hash table with 5 elements, and our hashing function is to take the key and mod it by 5. All right, and so we want to insert 2 and then some data. It's doing ellipse for the data. We don't really care. We're just focusing on the hash function. So we insert 2. It goes into index 2 because 2 mod 5 is 2. Great. How about 21? It goes to 1. Why does it go to 1? All right, we're doing great. 34 goes to 4. We're doing good. We insert 54. Why is this a problem? Yeah, so they have a collision. How can we solve this? What's that? Yeah, we could use a linked list, which is the first thing we're going to talk about. All right. Dealing with collisions, there's 2 common ways to resolve it. It's chaining, which I think is the more intuitive way to think about it, where a table entry contains a pointer to a linked list, and you just store all the items in that linked list. And then once you jump to the index, you search the linked list, and we're done. That's definitely the simpler way, in my opinion. The other way is called open addressing. Every entry only contains 1 key. If a new key hashes to it, which is filled, somehow examine other table entries you find until you find an empty one and put the key there. We'll get to why that gets very complicated very quickly next class. But let's just focus on chaining for now. All right, so for putting 34 and 54, notice now we have a linked list, so aka a chain. And we just add it to the bucket and we're done. Okay, great. You can insert 101 and do the same thing.
What is that, 12? That 1, 2?
Yeah, the 1, 2 is a 12. What's also funny is for some reason 2 is in bucket of 1. Yeah. Well, that's the new 12, man.
Gotcha. I remember writing like that.
Yeah. Good luck typing it.
That's gonna be tough.
I also like how 2 maps to 1 is what that doesn't make any sense.
And 101 is slightly to the right of that square.
Yeah. Yeah, yeah. Yeah, these.
And there's also the keys 2 and 3 and the right one are slightly separated.
At least those 2 are.
Oh, yeah, there's
same,
next-
they're the same, pushed over the same amount. But 54 is the other way.
Right. By the way, why did we add to the front of the linked list? What's that? Looks recent, okay. It's easier. You just update the head pointer and you're done. It's easier, and it's the same performance. Well, unless you, well, walking the whole linked list might slow you down, so you just add to the front and call it a day. All right, what is the running time to insert, search, and delete? Do they tell me? Insert takes O of 1 to compute the hash function and insert to the head of a linked list. Everyone good with that? You jump to it, and then you're just updating head. So you're not having to walk down the linked list or anything, you're good to go. So it's O of 1. Oh, good. Search. Proportional to the max length list length. Why is it that?
Because you have to go through the whole thing.
You have to go through the whole list, right? So if you had a hash table where everything mapped to the same entry, O of, well, it'd be O of n, where n is the number of elements. So that would be bad.
And over the number of indexes in the initial array.
No, well, if ever, we'll get to an example here in a bit. Delete, hopefully you can see it's going to be the same as search. All right. Therefore, in the unfortunate event that we have a bad hash, all n keys may hash in the same table entry giving O of n runtime. Please go to the example. Here we go. Here's the example, and we'll jump back in a moment. For example, let's assume keys are multiples of 5, and our table has 7. So 5, 10, 15, 20, 25, 30, etc., etc. Now as you keep adding those, you actually have an equal distribution, which is pretty good. But if m was 5, what kind of distribution would we have?
Everything in one place.
Everything would be in one place, which means when you went to do a search, what are you actually searching? O of n, because you're searching a linked list. Yes.
Is there, well, I take it there is a way to do it, but it would have to be multi-threading in order to have another process. Like once you add something in the background, it lets the user do other things, but there's a background process that sorts the actual linked list so that you can speed up the search.
Okay, if you have a sorted linked list, what search are you going to be running? Because you can't.
You can stop when you realize that what you're looking
Oh, I
for is
see.
greater than or less.
Okay, you could do it that. Sure, but I don't believe that's going to add much performance. Because what's your objective here if you have a linked list? How many elements do you want there?
It's few.
It's few as possible. In general, you don't want 2 or 3 max is what happens. So, keeping it sorted. All right, let's go ahead and jump back real quick. All right. Hopefully you can see everything depends on this hash function because you want it to be uniform hashing is the ideal target, aka every entry in the hash table is roughly the same, has the same number of items in it. So what's the best way to figure out a hash function?
Use somebody else's.
Use someone else's, great answer.
Use your keys.
Look at me.
The best way to what?
How do we come up with a good hash function?
Plan ahead.
Plan ahead, a big
Like,
deal.
I was gonna say, like, if you think about your keys beforehand, items you're gonna have, you can kind of like see what's gonna get.
Right, so evaluate what you have coming, yeah, so get some test data and figure out what's good, yes?
This one created by a professional.
Make sure.
The one in the STL.
Or something.
I like how the two answers are different but still correct.
I'm gonna drop it.
Yeah, unfortunately, there's no hard, set, fast rule to be to do this correctly. We just know what a good one is, which is one that aligns close to uniform hashing.
How does that work?
How's what work?
How does that work?
How's what work?
It's like, just a good person. He said like, what was it? I just forgot what he said.
Uniform hashing.
I don't know what you just said, but it was fantastic. Thanks. Helen.
You said like there's no good way to do
There's
that.
no hard and fast way to know you have a to come up with a good hash function, so to speak. But you can test it to see if it's good for the inputs you have in.
Oh, okay. I thought
It's okay. All right, so finding good hash functions, you want to do statistics on the key distribution, and then if your key was choosing the first letter of the last name, for this example, you'd probably have a lot of collisions, and that would be terrible, so don't do that. Most programming languages, like Java have hash functions built in. C++, kind of, sort of, it's part of the library. Aha! So choosing a hash function, what are some common ones? Well, the first one is just do the mod. All right, that one's nice because it's easy. Mod n in general n should be a prime number. They've just discovered through a lot of statistics and running around that if m is prime, you're probably going to have good distribution. Has to do with number theory and how division works. Multiplication method, they do this. You take the key, you multiply it by some fraction, you mod it by 1, then multiply it by the array size. And usually the sum fraction is 0.618. All right, how do we get that number?
Somebody found that.
Yes, statistical analysis. Good job. Exactly it. Why is this going to give you a range from 0 to the array size?
That's what you did.
Right, because you're modding it by 1. And is it ever going to give you array size?
No, because if 1 not 1 is 0, so
Yeah, exactly. Yeah, because you can't get 1, and it's always going to truncate. So you're not going to get the array size here. What does Java do? It shifts some things around, adds some numbers, XORs them, and goes on. By the way, do y'all know what shifting and XORing is?
No.
Not a clue?
Yeah.
Not a clue. All right. Let's go for a nice little